Today we're going to be talking about a second presentation for the thesis. First, I would like to introduce our colleagues, Zan, Murad, Mohammed Al-Hami, myself, Walid, and Nami. Our topic is strengthening concrete beams using carbon fiber reinforced polymers. And before we start, Nina will just distribute a sample of materials for you to look at. These are the sample of the sheets and the laminates that we used. Okay, so a quick outline of what we're going to talk about in the presentation. First, we're going to discuss the problem statement that we're trying to solve, and of course the objective and the scope of our thesis, the different methods that we're going to be using, the design for the steel as well as the mixed design for the concrete, the work that we've accomplished so far in the lab, the different types of processes that we used and the results, the problems that we faced during our thesis, and of course the updated time frame after our result. Okay, so basically the main problem is that the traditional method of bonding the CFRP, they're usually bonded at the bottom of the concrete RC beams. What happens is there's a common premature failure, which is called the crack-induced debonding failure. And this is what we're trying to reduce. The main objectives and the scope of our thesis, first of all, is to examine the effect of CFRP laminates according to their strength. We're going to be trying different methods and of debonding the CFRP in order to analyze the effects. Also, we're going to compare between them in order to find out which is the most effective method to debond the CFRP. And finally, of course, we're going to relate the experiment analysis that we have to the code provisions. Okay, so the method that we're going to be using, basically we're going to do 10 beams. They're full scale, they're 3 meters long, and have a cross section of 15 by 40 centimeters. Their strength, we designed them to be from 25 to 30 megapascal. The CFRP strips, they're going to be bonded in different configurations in each beam. And when they reach their full strength after 28 days, we'll be testing them for fracture and failure. And this will determine the effect of the CFRP laminates, how it affects the strength. And of course, for each cast that we do, we're going to do 6 concrete cubes, which should be tested after intervals of 7 days, 14 days, and 28 days. The first 2 beams that we're going to do are the control beams. Basically, they are without any CFRP laminates, and these are just acting as control specimens for the rest. The second 2 beams have CFRP strips at the bottom of the beams, and we're going to bond them using epoxy adhesive. And Muhammad will continue with that.
First we talked about the control, then we're going to have the 2 beams that are attached with what the industry considers the traditional approach, which is attaching them from the bottom. As we said, we believe the failure is going to be caused by the cracks instead of reaching the limits of the laminates themselves. So we decided to try different alternatives to how to attach them in order to try and increase the strength of the beam. So we decided for the second 2 beams, we're going to attach the laminates from the side, as you can see here. We thought this might delay the crack moving from the beam into the layer of the epoxy itself to try and reach the limits of the CFRP itself. We decided to have 2 more beams, 4 more beams, 2 attached from the side and 2 attached from the bottoms. And at the same time, we're going to add CFRP sheets as the ones we handed to attach them from the side. These should work as anchors and try to, again, delay the crack happening in the epoxy layer itself. These were the designs and calculations for us. We, while trying to find a design for the flexure capacity, it came out as the control beam should give us up to 10 tons. During testing, we found out that it gave us up to 16 tons instead. Going back to the calculations, we realized that we used, in the calculations, we used the steel as has an F yield of 360. Later on, we tested the steel and in the lab, and it gave us an F yield of 475 instead. So accounting that in, it should give us around 16 as we saw. We also have the calculations for the shear just to make sure that it wasn't gonna have shear failure. We're gonna test them on a 3-point load system. This is the configuration for it. We decided to do it this way to make sure that we wouldn't get like shear failure instead. We'd have a flexure failure. This is the design for the steel. We're gonna have 3 steel bars at the bottom and we're gonna have 2 steel beams from the top. We decided to increase the number of stirrups on the side. So we're going to have 18 stirrups, 7 in the first meter and 7 the last meter, and the rest in the middle just to ensure as a final measure that we will not have shear failure. I'll leave you with my colleague Nina.
This is our mixed design for the 10 beams, cement 400 per meter cube, cement 400 kilos, sand 649, aggregates 1205, and water 220. This is some pictures from the lab. Mixing the epoxy, how we attach the spring gauges to the steel, our formworks, and how we cured our beams and cubes. Because we have full-size beams, we didn't have the cure room big enough. To ensure the best results, we hired certified applicators recommended from BASF and Sika. It's a company called Best Solution to install the CFRP and sheets to have the best results. This is them grinding the beam to ensure better bonding between the epoxy. This is a box to install the epoxy on the laminates. This is how they attach it to the bottom and how they use the steel roller to fix the sheets. Accomplished work, we have 10 beams poured, cured for 28 days and tested to flexure to failure. 24 cubes were cured and tested at 7 and 14 and 28 days. CFRP was installed by certified applicators. 3 samples of steel were tested for tension in the mechanical lab. We will show now the results of all the cubes and the 2 control beams, while the other beams are still in the analysis phase. This is the results of our cube. We poured our 10 beams in 4 casts. First cast we had 2 beams, second cast 2 beams, third and fourth 3 beams at a time. We have one cube missing in the second cast because the cube after pouring it failed. We didn't test it. All the results are between 25 and 38 megapascal. In the testing process, at the beginning, we simply load the beam onto the testing area, and we chose to have 2 roller supports to support the beam. The beams were tested at 3-point load system, as shown below.
Okay, continuing the testing process, this is the test setup for every beam we did. We have a demic point in the top of the beam, the load cell, 2 strain gauges, and 1 LVDT. Every equipment of these has a specific measurement. For example, the strain gauges measure the strain in the steel bars. The LVDT measures the deformation in the concrete. The demic point measures the strain in the concrete. And the load cell measures the load applied every 0.5 seconds. And all of these are connected to the data acquisition system, which then produces the data sheet we're going to use in the analysis process. This is a closer look of the equipment we use. The demic point, the load cell, the 2 strain gauges and the LVDT. And this is the data acquisition system. This is a sample of the data sheet produced by the data acquisition system. We have 5 channels. The first one is the load cell, the demic point, 2 strain gauges, and the LVDT. As you can see, it has all the information we're going to need in the analysis. It has the units that we are going to use, the time, every 0.5 seconds, and the corresponding measurement. While testing, we wanted to record every experiment we did, so we used the video camera to capture all the testing process, which we're going to help us in the demonstration later on. While testing the beam, we were monitoring the beam, and we monitored the cracks that happens, and we just highlighted with the marker to help us demonstrate later. Let me show you a picture. As you can see, these are the cracks on the control beam, and it's concentrated in the middle span, which corresponds to our design, which is flexure failure. These cracks, later on, we're going to attach the CFRP laminates. They are going to move down and horizontally until it reaches the epoxy layer, and then the bonding failure happens. These are the results of the beam. The first control beam failed at 16.1 tons, and the second one failed at 15.7 tons, which corresponds to the design we have. Now I'm going to talk about the problems we faced and how we solved them.
We faced about 7 problems in working. Formwork, limit point, beam bearing failure, CFRP limits, shortage, CFRP installation, shortage of cubes, strain gauges. Let me explain each one briefly. The formworks, one of the formworks was not able to pour in, so we bought 2 more new formworks, so we could pour 3 beams at the same time and increase our productivity. The limit point wanted to fix our limit point on the front side of the beam from its center, but we did not do that since once we apply load, it's gonna buckle, so we inserted it on the top side of the beam beside the point load. The beam bearing failure. While applying load on the beam, we noticed the bearing failure from both sides of the beam, from the 2 edges. As you can see here, this is because we accidentally applied the load on the concrete cover, not the reinforcement. So to correct these mistakes, we shifted it on the reinforcement. The CFRP element shortage. After cutting the CFRP limits, once we ordered the CFRP limits, they gave us 1 wall, but this wall was 2 loads in 1 wall. So once we started cutting, we had about 2 pieces left. One is about 260 centimeter, and the other one is 60. So the 260 we used it to attach it on the bottom of the beam beside the 3 meter laminate, and the 60 we cut it into samples because we won't use it anymore. The CFRP installation, it took a lot, most of the time, not most of the time, to find the applicators for the CFRP until we found the best solution company recommended by Basf & Sika. The stirrup shortage, we increased our stirrups to 7 stirrups from each meter, at the first meter from each side of the beams to avoid the failure shear. So we ordered more stirrups. And finally, the strain gauges loss. While the CFRP applicators were working on the beam, attaching the limits and sheets, they cut accidentally 2 strain gauges from 2 beams. But luckily, we made the same consideration, so we put in each beam 2 strain gauges. And this is our time frame, as I explained before. The research took about 3 weeks, the beam design took 1 week, the material procurement took about 2 weeks, the pouring the design cubes take 2 weeks, curing the concrete take about 5 weeks, attaching the CFRP limits took 1 week, but it shifted and all the activities under it got shifted because the 1 week of the feast. Thank you. Any questions?
I didn't get exactly the structure, I'm sorry, but this was a control beam, and the control beam is fixed with CFRP with epoxy. مش كده؟ Sorry?
Control beam, we didn't attach any CFRP to the control beam. We attached it, we poured 10 beams, and we had 8 of them with the CFRP and 2 of them without.
Okay. So, are you using the CFRP as a repair material or as part of the original design?
Original design.
Sorry?
Part of the original design to strengthen the beam. We were not repairing.
So it's not as a repair material, it's part of the original design. And the advantage of it is what over a normal concrete, reinforced concrete?
It's strengthening the beam. It makes the beam able to extend more weight, several more tons.
So you're strengthening the beam without increasing the steel.
Yes.
So you're using that. Thank you.
No, I'm just asking about something you mentioned quickly. There are technicians that you have made use of to certified one, and I really understand and appreciate that, but I'm kind of curious, by the end of this work, if I ask any one of you to install the FRP in the same professional way that these people have done, do you think you'll be close to that, while it's too complicated?
It's very easy.
It's very easy.
الراجل ده بيعمل كده وانت تقول
Well, it's not too complicated when we do it, it's easy.
لا يعني it will be a waste that 5 of you are seeing people installing them and we don't grasp the way of doing it, because we know through several research at AUC here, and I know you know that, and I would like to commend Dr. Aiz for working with you heavily on this work, is that the surface preparation and the way this thing installed plays a significant role. It's not a minor one. So yes, you're right to get somebody professional doing it, but at the end of the work, I would love to see that شربتوا الصنعة منه مرة.
Yes, we videotaped the whole process.
Yeah, but videotape it, that's to see, but I want to see your hands doing it.
It's because we actually saw the previous samples and we saw how the CFRP just got detached from the entire sample. So we realized that having someone professional do it would.
Okay. And I repeat you my simple recommendation, maybe using the ultrasonic on the cracked or internally cracked or suspectedly cracked cross-section may give you useful information at no cost without much delay.
I kind of understood that the current methodology to apply the laminate sheet from the bottom has its drawbacks, so inducing the cracks from the bottom. And part of the objective is to find other locations in the beam to apply these laminates. Is that correct?
Yes. Yes.
If that's the case, do you have, are you just randomly selecting locations, or what's your plan? I didn't see a formal plan on the kind of experiments you could like to make.
The moment is at maximum at the bottom of the beam in the middle. So we put traditionally we put the laminate at the bottom. So when we try the alternative method, we put it at the sides and the bottom also to have maximum effect on the moment.
Any literature review in this regard that would recommend a different setup?
No.
It's basically by common practice. The most traditional method is at the bottom, that's what everyone used. But after speaking with our advisor, Dr. S, we came up with trying to put it on the side to see the ways it adds most. And of course, there's going to be more detail of the other deals in the last presentation because we hadn't enough time to put all the data.
What is the direction of the fibers when you put it on the side? What are the direction of the fibers when you put it on the side?
The laminates or the fibers?
Fibers.
They're rolled around. If this is the beam, you have the two sides at the end, they're rolled around it. If there's a picture,
It's shown from the two ends through the bottom on the other side. So from the top there are no sheets, but from the bottom there is. Just
so the fibers are parallel to the beam itself.
The fibers are perpendicular to the axis of the beam.
Yes. Yes. Parallel to the beam itself and perpendicular to the
Doctor, as you can see from the template, the sheets have only one direction to be installed.
That's what I'm saying.
Yes. It has to be in the horizontal way, in the vertical way. It has to be installed in the vertical way. It can be put horizontal.
Why?
Because it won't sustain any load.
I'm just want to explain that in terms of stresses.
It's how it's made. It's not stresses. It's made to sustain the load horizontally. Vertically, sorry. If it's
vertical or horizontal, in the direction of the fiber.
The direction of the fiber,
which is this way.
In this case, this way.
No.
This is a cut sample. It's not. We didn't cut. Yes.
This
in
is
this
the direction
case,
of the fiber.
Yes, in this
So
case.
what you do, you wrap it around the beam like
Yes,
this.
yes.
Right. Why don't you put it like that?
It doesn't make any, it won't differ.
Yeah,
Because
yeah, you won't
We're
different
not,
size.
we're not trying
Okay,
to.
right
build-
now, okay, you wrap the beam like this. Okay, I'm asking, why don't you put it like that on the beam?
Because wrapping that way, we're trying to use it as an anchor to attach the laminates together. So wrapping it around will stick the laminates to the beam.
Well, that's the reason.
Yes.
In this
What kind of stress are you trying to carry or resist in the beam? When you wrap it like that, what kind of stress you're trying to carry?
No, we will put it as an anchor to resist the load, to try to hold the laminate not to fall, to strengthening the bonding between the laminate and the beam.
No, that's not my question. I mean, if you wrap it around the beam like this,
Yes.
all right, you're hoping that this would resist certain stresses in the beam, right? Would, if they, for example, bending stress, shear stress, normal stress, what?
I guess it's shear, because most of the thesis work is to resist the shear.
Okay, that's what I want to hear, to resist the shear. And that's why the direction of the fibers is set to do that.
Yes, because the cracks go to the bonding and it goes this way, so this configuration and of course the laminate himself, you resist the shear. And that's mainly the main problem.
I think you should also, find out if you put it this way, on the side.
Just
might-
not roll around just the
Yes,
slide it here.
right. I mean, look at it at least analytically. I'm not saying do
Yes.
that on the experiment. You,
No, actually, they should do it experimentally as well.
no, the beams are too big, and I think it's going to be. So,
That's a very good idea.
but I think if you have it in an analytical model, it will give you a lot of explanation to how this fiber would work.
We'll try to put it in our last presentation, hopefully next semester, so we will continue with
Okay.
actual experimental work.
I like the idea of Dr. Safwan, but can you tell me why? Why do I like it? If you put the sheet on the side of the beam, what is the difference? You see, the thread you attach to the side of the beam are 50 millimeter. What is the depth of the sheet?
1.2.
No, no, no.
The sheet.
The width of the sheet. If we put it like Dr. Safwan is saying on the face of the beam.
50
So what are the
50 centimeters.
50 centimeters? So is that better? Is that
Because
better
it
than
covers a bigger area, you mean, so.
bigger area? Are you sure it's bigger area?
Yeah, it's, because the laminate,
Let's think thickness.
on the surface area,
Yes, thickness of the sheet is
very small, 1.2 millimeters.
1.
Yeah.
1 is the strip. What about the sheet?
The sheet itself, very, very small.
Point 0.12.
0.1 or 2.2.
So how can we treat that? If I want you to execute Dr. Safwan's idea and put it on the side, what should we do?
Put several layers in on top of each
Yes.
other. So, because of course this cost is going to be it's very expensive. So we also try to consider the cost because we also, as well as strengthening the beams, we don't want to put an extreme cost to it.
Okay, let me ask you something else. If we did Dr. Safwan's idea and put one layer horizontal,
Yes.
then wrap it with one layer vertical. Don't think about cost because when you do that strengthening, you do it usually on bridge beams, right? So you're saving something which is really expensive. So if we put one horizontal and one vertical, then one horizontal and one vertical in 3-4 layers, will we catch that crack?
Yes, we might.
I don't like the yes, but I like we might. But I don't like yes.
I don't think it will make any difference.
We don't know. But it's a good idea.
We leave it for the next semester for the other students to try to experiment.
Next was for other students.
For experimental, you will put the data and
For
then
other students.
Now I have one question. You tested the control beam. You said that you measured the deflection, did you plot the load deflection curve?
Still in the analysis process.
Yes, we have the curves for the control beam and also for the, we did all the experimental work for the 10 beams, but we included here also very small data about the control beams, just because we're saving it basically for the presentation to put the curves.
And to compare it with all the other beams.
So you did not show the, although it is connected to data acquisition system, you should have
Yes, we
some
thought it would,
results.
I know, we thought it would be just a better as a comparison to see it next to other, the rest of the beams, so you can compare it better between.
When you are attaching the laminates to the side and you are attaching it to the bottom fibers, which one do you think will give you higher strength?
I think the side, because the bottom, when we applied the load, all of the bottom ones, after reaching a bit more load, they cracked and they fell off. So the side would still, I think, would stand a little bit more because of this factor.
It's because the concrete at the bottom fibers is more cracked than.
Yes.
So it is now attached to sound concrete, so it will have better effect.
Yes, the control beam, it showed that the cracks were very high at the bottom as compared to the upper at the side. So that's why it reaches the bottom first, so it falls off and you can't withstand it.
Now, do you think that applying these fibers will have an effect on the stiffness, not only the strength, but it wouldn't affect the stiffness much? I mean, what's your expectation for
I
that?
don't know about the stiffness. Maybe the stiffness could be affected more by the wrapping around the sheets, but I'm not sure about the laminates themselves.
Let's wait and see then. Stiffness, you know, should affect.
One last question, if I may.
Yes.
Where did you get that steel from?
Steel?
Steel portion.
From the fifth.
We got steel with 475 meter scale beams.
I'm surprised.
They tested it on mechanical engineering. Did you get it from?